So yeah, this is going to be the first of the 3 lecture series shared by me and Anna. And Anna is going to give the second and third talks. And well, here I am. So yeah, this talk is about construction of automorphic Galois representations. So well, did I thank the organizers, by the way? Oh, I thank the organizers for inviting me here to speak. And well, blah blah blah. Okay, getting back to the point. Yeah, so this is about construction of automorphic Galois representation. So as you may know, in the Langlands reciprocity, there are 2 sides, automorphic and Galois side. And this talk is about going from automorphic to Galois, and then the rest 2 talks will concentrate more on how to go from Galois back to automorphic. So from Galois to automorphic is about this modularity in the title, in the subtitle. And we are going to underline the role of Shimura Varieties. So that explains the title, Shimura Varieties and Modularity. So let me get into the business. So here's the plan. My talk has 4 parts. And part 1 is to state the main theorem on in the automorphic to Galois direction. And there are 2 settings with elliptic coefficients and torsion coefficients, such as mod L coefficient. And the second part, well, as a step toward the main theorem, I like to prove the elliptic case for self-dual automorphic representations. Eventually, we want to get to non-self-dual automorphic representations as well, but this is a key intermediate step. And here, you're going to see the use of the Langlands cut width method, which was briefly discussed in Morel's lectures. So, and the third part is on perfectoid Shimura varieties. And well, in short, we are going to see that Shimura varieties at p to the infinity level are perfectoid, or should be perfectoid in generality. We are going to see Hodge-type Shimura varieties, but something like this should be true in general for even non-abelian type. But this is the slogan, and then, well, or principle, if you like. And the last part is on the construction of the torsion Galois representation using results from parts 2 and 3. And here the key word is p-adic congruences. That's how you kind of reduce to what's already proven. So yeah, that's pretty much a good summary of my talk. So if you don't get anything more out of my talk, that's fine. You just try to remember what's on this page and you're still good. So you can go to sleep. But if you're interested in more, then yeah, now you can listen to me. And by the way, the first 2 parts will be given out of slides, and the last 2 parts will be given at the blackboard. And I chose this way because I want to go over parts 1 and 2 rather quickly. And there's some notation, but also it's not something I want to emphasize too much, but I want to leave more time to discuss part 3 and 4, especially part 3. And some things in part 3 will, I think, reappear in Anna's talk, so I think that's important. And obviously, part 3 and 4 are more recent. Okay, so here's the main players, and yeah, it's a boring time. We need to see some notation for the rest of my talk. So F is a number field, L is a prime, and well, N is a positive integer, and S is some finite set of places. Basically, it's finite set of bad places, including those over L and infinity. And so that K upper S is just the product of hyperspecial subgroups in GLN. And so we basically keep things unramified outside S. So yeah, here's some sets I want to define. So in the automorphic side with characteristic 0 coefficients, well, you can consider the notion of algebraic automorphic representations, or more precisely, C-algebraic and cuspidal automorphic representations. So, well, I'm not going to define C-algebraic carefully, but just the notion of algebraicity, which depends only on the Archimedean components. And roughly, it means that the infinitesimal character of every Archimedean component is integral. A priori, it's complex, but it's integral, but up to some shift by some half sum of positive root. But if that doesn't make sense, that's fine. It's just some notion of algebraicity. And there's also a smaller subset consisting of regular algebraic guys. And regular means the infinitesimal character is regular. So it's stabilizer in the vowel group is trivial. So, all right. So I'll just, to remember the notation, I'll put this in here. Well, eventually the theorem will be only about the regular case, so I'll just remember that guy. And in the Mod L case, well, classically you have this automorphic definition of automorphic forms, but that doesn't really work. Mod L, for instance, if you don't know how to define the action of the Archimedean group on an elliptic or Mod L space, so rather here a good substitute turns out to be you consider the cohomology of locally symmetric spaces for GLN in this case, and keep things unramified outside S, and then you have this Hecke algebra action, unramified Hecke algebra, because you're using this hyperspecial subgroups away from S, and this Hecke algebra, which is a commutative algebra, acts on the cohomology. So any eigencharacter for this commutative algebra action will be put into this set I call HE. So Hecke eigencharacter or Hecke eigensystem. So that's the guy we are going to consider for stating the theorem. Okay, so far so good. And on the Galois side, well, you have obvious candidate because, well, we are not doing anything fancy like, well, coherence shifts on the moduli space of something. So it's just the honest Galois representation. So I chose the notation G, script G, because it's easy to remember, G for Galois. So either with QL bar coefficient or FL bar coefficient. So good. So these are just upper S means always away from S or unramified away from S. So I hope it's easy enough to remember. N is a positive integer, F is a number field, and well, A for automorphic, G for Galois, well, HE for Hecke eigencharacters. So, well, I think we are ready to go on. So, right, so I just recall some notation. And what is the conjecture? This is the key conjecture I like to discuss in this talk. And well, for every F, and well, at least in the elliptic case, because the automorphic representations have coefficients in the complex field, you need to choose an isomorphism between C and QL bar to make it precise. Don't worry about it too much though. And we have this conjecture in the elliptic case and in the torsion case. So in the elliptic case, basically it means that you need to have an arrow so to go from automorphic to Galois. And conjecturally, you should have this arrow such that it's compatible with the unramified local Langnans at almost all places away from S. And you can say more things at the set of bad primes, but I'm not going to state it in this talk. I'll just concentrate on this compatibility away from S. Okay. And similarly, in the torsion case, the statement is, again, from automorphic, you can get a Galois representation with coefficients now in FL bar, but more or less it's the same deal, except that, well, the condition is that because in the eigencharacter, you don't exactly, at least in this setup, you don't exactly have a representation of, G of QV or something, GLN of QV or something, but rather you just have an algebra character away from S. So, but out of this, what you can do is, well, you have a map from the Hecke algebra into FL bar, so you can take the images of various Hecke operators at V, and then these are supposed to be Hecke eigenvalues for Hecke operators at V, and then out of this you can just concoct a Hecke polynomial, which should remember, well, it's model analogs of the Satake parameters. And the condition is that this is equal to the Frobenius characteristic polynomial. So it's not a complicated definition, but it's basically the mod L analog of the condition in number 1. So Okay, good. So one way to think about this Hecke eigencharacter is just it gives you a string of Hecke eigenvalues or a string of Stockhet parameters. That's one way to think about it. Okay, so I mean the conjecture is due to various people, mostly to Langlands, but then these various versions have been developed due to Clausel, Fontaine-Mazer, and also in the Mod-L case, I think Ash was probably the first one to propose something like this, something like part 2. Anyway, well, and there are surely other people who contributed, but let me now make some remarks on the conjecture. So as you can see, you can uniquely characterize these maps, or at least for given each pi or m, well, you can uniquely determine the corresponding Galois representation up to isomorphism. This is done by the Chebotarev F density and Brouwer-Nesbitt. So it's certainly possible. And you can ask about the images of these maps, at least conjecturally, and it's believed to be irreducible Galois representations. Irreducible should correspond to cuspidality on the automorphic side. So irreducible Galois representations, which are drawn at all the places above L. At least conjecturally, that should be the image of this map. It's probably a little bit less clear in the Mod-L case. At least one necessary condition is believed to be, well, the Galois representation should be odd at all the real places, but then is that really sufficient? Well, maybe you have some experts in the Serre conjecture in the room, so you can ask them. But it's basically kind of belongs to the topic of Serre conjecture. And, well, should be obvious because I stated this to 2 different parts, but one doesn't imply 2. And, well, I mean, there are some reasons, but of course, I mean, one reason is that not everything in here comes from taking mod L of here. So that's basically the main point. And actually, we have some numerical results saying that you have more mod L Hecke eigencharacters than characteristic 0 analogs. So certainly, you don't expect to prove 2 from 1 by some very simple method. And another thing is that, well, you'll see this in Anna's talk, but this Galois representation rho bar m, why do I write it as rho bar? Well, there's also rho m that you're going to see in Anna's talk, which is kind of lifting of rho bar m to some Hecke algebra. So you're going to see that. Not kind of universal. Well, in some sense, you're like automorphic. In some automorphic sense, you could say so under some restricted conditions. But yeah, but it's just the Galois representation valued in some Hecke algebra, localized at M, the corresponding maximal ideal for the Hecke eigencharacter. And then, yeah, surely, well, you have this kind of conjecture for general reductive groups, and in the Aledi case, it was carefully written down in a paper by Bazard and G. And in the Mod-L case, I'm not sure if it's written in complete generality. I don't know if anyone knows, but in any case, of course, you can just write down, just, mimicking what they did for general reductive groups with Aledi coefficient. So yeah, you can surely give a conjecture, well, because you don't need to prove it. Right, so yeah, what do we know? So that's basically the goal of my talk, which is to explain how this can be proved. So the important condition is that f is totally real, or CM. In that case, part 1 is true, proven for regular algebraic cuspidal representations. And part 2 is also proved without any further condition. And it might sound asymmetric, but actually they are kind of symmetric in the sense that this Hecke eigencharacters or Hecke eigensystem, these are analogs of regular algebraic representations rather than just algebraic cuspidal representations, because, well, Because basically these guys are those algebraic automorphic representations which contribute to cohomology of locally symmetric spaces. And I mean, there's some results which go slightly beyond the regular case. But yeah, in this talk, I'm not going to talk about it. I mean, there you can go slightly further by using coherent cohomology of Shimura varieties rather than just Betti et al. Cohomology, but that's kind of orthogonal to my goal, so I'm not going to say any more. Are there questions up to this point? Okay. Then, yeah, I'll just give the order of proof. So here's the theorem we would like to prove, right? Then I'm going to define some subset in this regular algebraic cuspidal set given by the conjugate self-duality condition. And conjugate self-dual means that, well, the contragradient is isomorphic to its complex conjugate representation. So that's pi composed with C. C is acting on the group GLN F. So this complex conjugation is, of course, trivial in the totally real case, so you just ignore it. But in the CM case, it is non-trivial, well-defined order to automorphism. So you can define this subset. And then the idea is that you prove the theorem first in this case. So that's what you do. And you do this with elliptic coefficients. So in the more traditional setup, so to speak. And then, well, what do? Well, you prove the torsion case. And I'm not going to say too much about the mod L to the M case, but the argument is very similar. So you take care of the mod L coefficient, namely FL bar coefficient, but also you can deal with Z mod L to the M coefficient in a pretty similar way. And once you do that, then you can just glue things together to get the regular algebraic cuspidal but non-self-dual case. So yeah, to do this, you need to use this pseudo-determinant or pseudo-representations. But that's basically how to go about doing this. So in my talk, I'm going to explain number 1 and number 2, namely, well, I'll briefly explain, but I would rather not spend too much time on explaining how to do the self-dual case, and then I'll try to leave more time for the torsion case. Okay, that's my plan.
So by superscript S, you mean the level is only at S?
Yeah, so upper S means, yeah, everything is unramified away from S, and for level subgroups, you're putting hyperspecial away from S. Yeah. Okay, good. So yeah, so here's the theorem in the self-dual or conjugate self-dual case. So basically, yeah, we're saying that in this conjugate self-dual subset, we have this global Langlands map. And maybe I don't have to write down anymore such that blah, 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 and blah, blah means, well, you have some compatibility away from the set S by unramified local Langlands. And as I said, you can say more about what kind of Galois representations you're getting, like Hodge-Tate numbers or image of complex conjugation, and, well, things at bad primes, but never mind. I'll just try to explain how this can be constructed and how we get some properties away from S. So there's some not completely elementary, but somewhat standard reduction steps. So you can reduce to the CM case from the totally real case. So you can assume that F is CM. And then if you denote F plus by F plus, the maximal totally real subfield of your CM field, then you can also assume that F plus is not Q. Sounds like a small thing, but it's helpful because you can basically assume that you're working with compact Shimura varieties. And the significance of the conjugate self-dual condition is that for these guys, you can access by using unitary groups. A priori, you have conjugate self-dual representations on GLN, but yeah, you can basically study them using unitary groups. So, and what kind of unitary groups? Well, here's the guy. Well, you want to consider the guy over F plus, the totally real field, with respect to some Hermitian pairing, F over F plus in n variables, so that it's an outer form of GLN, so kind of close cousin of GLN. And you want some condition on U so that you have some pleasant consequences. So you have, oh, by the way, I mean, in the classical story, you are going to see some unitary similitude group. But I'm going to ignore similitude always. And one reason is that it's better for exposition. And also, nowadays, if you're happy to work with abelian type Shimura varieties, then you can actually work with honest unitary group rather than unitary similitude groups. So don't worry about any similitude. But this condition you have seen in Morel's lecture. And the reason is that, I mean, this basically has two, I mean, it helps us in two ways. First of all, imposing this signature at infinity, you get a compact Shimura variety because F plus is not Q. So you have at least one infinite place where your unitary group is anisotropic. So namely signature 0, n. So you get compact Shimura variety, maybe, yeah, compact. And also, you want to realize the expected Galois representation rather than some wedge power or some tensor product thereof. And that's basically done by this condition. If you really keep track of what kind of highest weight representation of the L group you're getting out of this. So that's good. And the second condition is that it's a bit technical, but you want the unitary group to be quasi-split at all finite places. And the reason is automorphic. If you don't have this condition, that somehow you're going to have some sort of local obstruction for this automorphic descent, which is the inverse of the automorphic base change from unitary groups to GLN. So yeah, it's just kind of general philosophy, and also we have some precise statement that if it's not quasi-split, then somehow there's an obstruction. Namely, in the final result, if you don't have this condition, then you're going to have some, you need to make some local hypothesis for the capital pi you begin with. And you don't want that. So that's basically why. So here are the conditions on my unitary group. Now you're in the business. You can start the construction. And in short, these are the main, the skeleton of what's going to happen. You start from this automorphic representation pi, conjugate self-dual. Because it's conjugate self-dual, you can descend to some automorphic representation on a unitary group. So that's a little pi. And then once you have little pi, then this little pi can interact with the Shimura varieties for the same unitary group U. So you can take the isotypic part for the finite part of little pi. So that's pi upper infinity. This guy means it's the finite part of pi. Then you take the piece of étale cohomology of your Shimura variety with this isotypic part, because the étale cohomology has this interesting elliptic Galois action. So that's what I'm doing. But then the coefficient will depend on the Archimedean parameter for pi. So the coefficient local system will be chosen depending on the Archimedean component. And then you take this piece in the elliptic cohomology. So you're going to get a finite dimensional Galois representation out of this. And in this case, the Shimura variety is conveniently defined over F. So you have an n-dimensional representation. Well, not a priori not n-dimensional, but some finite dimensional Galois representation over F. So that's the construction, roughly speaking. But then let me say a bit more about this. So the first step is, as I said, this is what's called the automorphic descent, or the inverse of the automorphic base change. The correct direction is you go from U to GL. GLN, but you just take some pre-image as far as you know that the pre-image is non-empty and it's far from unique in general, but that's fine. You can just choose one, or in practice, you can also just take the sum over everything in the pre-image. As far as it's non-empty, you're good. So this is where we are using the condition that, secretly using the condition that U is quasi-split at all finite places. And the second point is that, well, so you starting from your capital pi, you arrive at some finite dimensional Galois representation, but why is this the Galois representation you want? The main point is you need to show that this Galois representation satisfies whatever compatibility you want. Like, in other words, the Frobenius action on this guy should have something to do with the stochastic parameters of the capital pi or little pi. And the Langlands-Cotwitz method is exactly showing that. So that's exactly the method showing this. But on the other hand, it was a little bit explained in Morel's talk. And here I'm not going to go into the detail of this method. So let's believe that the method works. OK, so that's all I say about this. But then I can't resist making one remark, which is there is a byproduct of this argument, namely the Ramanujan conjecture for the capital pi. So Ramanujan conjecture basically says that the local components of a cuspidal automorphic representation of GLN are tempered, or essentially tempered. This you can deduce basically out of this picture because, well, I'm dealing with compact Shimura varieties, so actually the Frobenius eigenvalues here are, well, Weil numbers by the Weil conjectures. And in fact, if you make this argument carefully, then they actually all appear in the same degree, in the middle degree of the cohomology. So as far as you can make the Langlands-Cotwitz method work, then it means that the stochastic parameters are basically Frobenius eigenvalues in the middle degree cohomology. So that way you can basically show that the Ramanujan conjecture holds for the capital pi. I mean, this kind of strategy was already used by Deligne when he proved the Ramanujan conjecture for GL2 for classical modular forms, and pretty much the same idea. Okay.
But
yeah.
Do you prove it for almost all places or for all places?
Yeah, a priori, almost all places, but then actually you can prove this for all places. Yeah. At infinity, it was already proven by Clausel, but then at finite places, yeah, you do this, but then you need to do this more carefully at ramified places. Okay, so I could have stopped there and just wrap up part 2, but that would be a little dishonest. So at least I'll say that there's a problem in executing this. And the main problem is, I mean, it seems not so serious a priori, but turns out that such a unitary group only lives in paradise and it doesn't exist in reality if n is even. So there's some parity obstruction, local global obstruction for finding this kind of unitary group. It's an order 2 obstruction, so it doesn't seem like very serious. On the other hand, I don't know of any simple trick that gets us out of trouble. There's no simple reduction argument. So when such a U doesn't exist, you need to think about some other strategy. So I'll just mention 2 solutions very briefly. So one solution found first was that, well, use endoscopy. Somehow this kind of obstruction doesn't exist when you have an odd number of variables. So you go from, when n is even, you go from un to un plus 1 by some endoscopic transfer and then construct Galois representation there in the cohomology of Shimura varieties for un plus 1. But then you need to really study the étale cohomology in the endoscopic part in some sense. But you can do it. This is partly made possible by people's work on the fundamental lemma and so on. But then that still misses a handful of cases. So you need to really, for a complete result, you also need to make some congruence argument using eigenvarieties for certain unitary groups. but that can be done and was done. Another method, if you don't care too much about reified places, I mean, there's another way, which is, well, in this case, you can also give up the condition too. You give up the condition that U is quasi-split at all finite places, but allow it to be something else. Then you can avoid the obstruction. But then in that case, what you can do is, for instance, what that means is that in the final theorem, you're going to have a statement like, if the capital pi, the automorphic representation is, say, essentially square root integrable at one place, then you have the theorem. Something like this. But then you can reduce to that case by some congruences, some other types of congruences. And here you can use some type theory to do this. You can even make it super cuspidal at one place. And then, yeah, you're kind of back in business. You can just apply some older result, which was already known by Clausel and Cutwit. So this kind of congruence argument is written down in my paper with Jessica. And you can also use the appendix by Raphael when p is small. So you can cover all primes p. So yeah, so there are some solutions for this, but then, yeah, you need to do some further work. Are there questions? Cool. So that wraps up part 1 and 2. And yeah, now I'm actually going to switch to the Blackboard and slow down a little. But the good news is that you don't need to remember anything. All you need to remember is here, but you don't even need to remember much about the notation. So yeah, well, if you fell asleep, you can wake up or just continue to sleep. But yeah, what you're going to see is, well, now I'm going to go into the p-adic geometry of Shimura varieties. And especially you want to show that Shimura varieties at p infinity level are perfectoid. And if you want to remember just 2 keywords, then anti-canonical tower and Hodge-Tate period morphism. And in part 4, when I get to the construction of torsion Galois representations, I'll just make this one point. Why is this very different and also not obvious? Why? Well, really the basic fact is that locally symmetric spaces for GLN are not Shimura varieties. And somehow this has prevented people from studying this case using the étale cohomology of Shimura varieties. Because the most obvious guess is that, I mean, by using some Shimura varieties and studying their elliptic Galois representations in the étale cohomologies, somehow you can construct this. Or in this case, you take mod L coefficient of the étale cohomology. But somehow this doesn't work because locally symmetric spaces are not even L-direct varieties unless n is 2 and you're over a totally real field. So you need to do something else. But yeah, basically here you make the connection with Shimura varieties using some topological Borel-Serre compactification. But I'll get to say more about this. But it's just to keep in mind that it has some initial difficulties. Okay, so I think this is a good time to switch. And should I, or I don't know, maybe I can just turn it off. Or, even better, I can open my, I should stop screen share, right? Or even leave the Zoom room. And just in case I have my talk notes ready, but anyhow, well, let's see. So part 3 is about perfectoid Shimura varieties. Let's see how well this transition goes. So for stating results, I can assume that Gx is a Shimura datum of Hodge type. But mainly I'll talk about the Ziegel case because it's easier to explain, and also logically that case is proven first. And some more notation. So Shimura variety with level k upper p. K upper p means always away from p. So upper infinity means away from infinity, namely finite adels. And star, if I put a star, that means minimal compactification. Running out of space. Sorry about that. So you have this Shimura varieties, and this is like what I refer to as P infinity level Shimura variety because I took the limit over all open compact subgroups. And of course, maybe I don't have to emphasize, but K upper P is assumed to be sufficiently small, so that you really have schemes. And you can associate adic spaces in a similar way. And I'll just say that this guy is now a limit of these guys. But then, well, a priori, you don't know if this is representable by an adic space, if this projective limit may not be representable by an adic space. So I just think of it as a projective system of adic spaces, which is fine. Well, eventually I'm going to show that this is a perfectoid space, but at least a priori. And from the Shimura datum, I can produce up to conjugacy a co-character of G. There is a standard way, and then this allows me to define the flat variety, which is basically the G modulo some parabolic subgroup defined by mu. Roughly speaking, it's the stabilizer of some sort of mu filtration if you have an underlying vector space. So I'll just say that in the Ziegel case, when Gx is a Ziegel Shimura datum and you have a Ziegel modular varieties, in that case, this guy parameterizes maximal isotropic subspaces of your underlying symplectic space. So that's all you need to know about this flat variety. Okay, so here's the theorem. So this theorem is due to Scholze and also in part Caraiani Scholze for the target space of Hodge-Tate period morphism. So simply put, the first result is that this guy is a perfectoid space. Well, to say this precisely, well, you need to give a more careful definition. So you can either pass to some category of functors or maybe category of diamonds and take the limit there. But, well, for us, a more useful definition is that the underlying topological space is really homeomorphic to the underlying limit of the underlying topological spaces of this guy. And then, well, basically on the level of algebras, well, the direct limit of the underlying algebra has some dense image in the algebra here and something like that. But don't worry about it. Well, if you're interested, you can look up the paper by Scholze-Weinstein, and there's a careful definition. So I'll just say this, and then, well, this guy comes with an action. So away from P and infinity, and also at P. And here, of course, to make this sense of this action, if K upper P varies, then I can make this adelic group act, but also GQP act, because I'm taking limit over K lower P, all the open compact subgroups of GQP.
So you fix the level away from P, right?
Yes, so here I fixed, but then you can also vary level, and then you can consider the adelic action. But on the other hand, for the construction of torsion Galois representation, I can keep things unreified away from S, some fixed finite set S, and then only vary there. I mean, I don't actually even have to vary much in that case. I just keep K upper S fixed. Because there I only care about the action of the unreified Hecke algebra. Okay, so here, the second part is that, so I have Hodge-Tate period morphism. Oh, by the way, I forgot to say, but I'll take the base field CP, which is basically all I need. And in terms of the previous notation, I'm taking P equals L, so any L before will be P, and that's fine. And yeah, these adic spaces will be considered over CP, although you can make things define over smaller field. That's all I care about. And the Hodge-Tate period morphism is going from here to the flag variety. And there's this action. And I like to say that it's equivariant for this action. In other words, the Hecke action away from P is equivariant with the trivial action on here. But then for GQP acts in an interesting way on both guys, and then also it's equivariant for the GQP action. So, right, and well, what this morphism does is, well, there's a reason for this naming, namely it reads off the Hodge-Tate filtration, so such that, for instance, on CP points, what it does is, well, you have some polarized abelian variety, at least in the away from the boundary, you have polarized abelian variety and some possibly extra data. It goes to the Hodge-Tate filtration. So what is the Hodge-Tate filtration? Well, so you take the p-adic Tate module and then tensor up to CP, and then there is a distinguished subspace given by the Lie algebra of A. But then, well, you need to twist the coefficient by choosing some p power roots of unity. So that's what I call by 1. Then it's a subspace, and it turns out that, for instance, in the Ziegel case, this guy is a maximal isotropic subspace, so it defines a point on the flag variety, and everything makes sense. So that's basically what the map does. And the main theorem I'd like to explain in part 3 of my talk is how this works. Okay, are there questions? Yeah.
Is any of this known or expected outside of Hodge-Tate?
I think, yeah, it's already known in the case of abelian type by, I don't know the most recent result, but Shu Shen, I think, proved, it constructed a Hodge-Tate morphism for abelian type Shimura varieties, maybe, but didn't extend to the boundary. And I'm not completely sure about that, but I think that's what he did. And then he also proved its perfectoidness. But outside abelian type Shimura varieties, I think this is well expected, and so is this one. But this is maybe p-adic Riemann-Hilbert correspondence by maybe Shinwon and Lan and Liu, and who is the? Yeah, Han Shan-Diao and Shinwon Zhu. Yes. So by this, some p-adic Hilbert correspondence. But do you also have the map extended to the boundary?
Minimal compactification. Probably Kai-Wen.
Okay. Maybe you can ask Kai-Wen whether it can be extended to the boundary. Okay. If he's watching this at all, then okay. He can answer it right away. But yeah. So yeah, it's maybe I should. It's good to write down the names, by the way. So, in general. So, okay.
Sorry, but the first result is not known for general. Just we just have that, right?
So far as I know, yeah, it's only known for abelian type, but not in general. But I think it's expected. Yeah. Okay, so now I have some challenge. Right, so let's prove this, but then maybe I have time for this. So I'll mention some two examples, because probably if you're like me, then I wouldn't know how to prove anything is perfectoid. So, but without even knowing the definition of perfectoid, here's one way to show it. So I have this adic space, SPA CPT, OCPT, and whatever I wrote down, it's meant to mean the closed unit disk in p-adic geometry. So it's basically you're writing down a power series converging on a closed unit disk. So that's what I'm doing. And then you can take some sort of limit. What is the best way to write down? Maybe I use a different variable. Yeah, but then transition map is sending S to S, upper P, or pth power. And you take the projected limit, then basically saying, I like to say that this is a perfectoid, or perfectoid closed unit disk, perfectoid version of the closed unit disk. And well, if you want to be precise, then you can represent it by, well, something like this. And the intuition is that, well, what is this transition map? It's just the p power map, and it's just the degree p covering, which is reified only at t equals 0. And then you're just taking pth power map, and by taking the limit, you're extracting a lot of p power roots of things, and then that's what it makes it perfectoid. And that's basically the model that we like to follow to show that in our situation, which is much more complicated, but still we want to use this model to show that it's perfectoid in some smaller scale. So I'm like to explain how this kind of idea is used. It's going to be used in the very first step, but the key takeaway from this example is that if you take the limit over transition maps, which is kind of relative Frobenius, then the limit is going to be perfectoid. This is kind of the basic principle. Okay, that's what's happening in this example, and we are going to see that something like this is going to happen in the geometry of Shimura varieties. Okay, so all right. So how do we get started? I'll concentrate in the Ziegel case because, well, in general, you prove the Ziegel case and then deduce the other cases from the Ziegel case. It's much simpler to, the latter part is much simpler. So we take G to be GSP2N, and X is some Ziegel half spaces. And I should say this at the very beginning, I'm going to ignore any issues with the boundary because, I mean, you need to do some hard work to extend the various constructions to the boundary, but it's already complicated without worrying about the boundary. So that's my choice. And well, I need to also set up some notation. So there are some distinguished open compact subgroups in GZP. So you have this gamma 0 and gamma where m is greater than or equal to 0. And then, well, as you can imagine, basically it's a block upper triangular thing, and then the trivial thing modulo p to the m. So you have these open compact subgroups. Okay, so what can we do with this? We can now start from this. That guy is like p infinity level, is at the very top. And I can also write it in this way, in the sense that, well, when I write something gamma p infinity, I just mean that something, I take something gamma p to the m and then just take the limit. That's so because gamma p to the m, they form a cofinal system in this limit. So when I take the limit over just gamma p to the m, then I just get the p infinity level Shimura variety. So they're same thing. But then I'll just, for convenience, I'm going to drop k upper p from the notation. So I have this, and then I have the bottom. You put no level at p, so it's gamma 1 or gamma not 1. And then I like to consider some open affinity subset of this guy given by epsilon. So what does epsilon mean? So epsilon means the locus where, well, you can define the notion of Hasse invariance, but in terms of the moduli theoretic description, in terms of the abelian variety. But yeah, if you're not familiar, that's totally fine. It just means this measures how ordinariness. So when epsilon is 0, then, well, 0, then it literally means the ordinary locus. But then I like to choose epsilon greater than 0 and not too big, maybe less than 1/2 or something. Then this is the ordinary locus. And this is like slightly larger than the ordinary locus. So some strict neighborhood of the ordinary locus that I'm considering, but it's still some affinoid. Maybe I'll affinoid. So the basic picture is that I'm not good at drawing pictures, but if you have, well, this is pretty lame, but if this is like ordinary locus, then, well, that's where epsilon is what's given by epsilon equals 0. Then, yeah, by allowing epsilon to be positive, you're kind of getting a little bit inside. And this is kind of the cartoon in the modular curve case where you have ordinary and supersingular. These are like supersingular disks. And then you're allowing a little bit of supersingulariness, but not too much. So you allow things to be slightly non-ordinary. That's what you're doing here. And then now we can really start to play a game. Pardon?
This thing is not a phenoid, right? You have to take some phenoid open.
The epsilon neighborhood is going to be a phenoid. I think it.
On the whole Shimura variety?
No, not the whole Shimura variety, but the epsilon neighborhood. Not the whole Shimura variety is certainly not going to be affinoid. Yeah, but it's.
But you're taking the epsilon neighborhood on the whole Shimura variety, right? You're taking the epsilon.
Yeah, well, Yes, I think it is going to be aphenoid, yeah. I mean, it's basically the analog of the algebraic. So the Hasse invariant is, if I'm not mistaken, the Hasse invariant is a section of an ample-line bundle, and basically where the non-vanishing locus of the Hasse invariant is therefore affine, and it's basically the analogous fact in p-adic geometry that something like this will define an aphenoid. On the other hand, also I kind of set this for safety that I'm going to ignore the boundary, which means that I'm going to actually confuse three different things, which is the compactified Shimura variety, and then the Shimura variety away from the boundary, and then even smaller open subset, which is the good reduction locus. So I'm going to confuse three different things, but that's it. I think it is aphenoid. Okay, so what do you want? Well, so step one is now I'm ready to build this anti-canonical tower. And yeah, oh, it went far away. Oh no. I don't know what's the best thing to do. Should I just write it again? Yeah. So let's see. Yeah, this is a little bit embarrassing, but well. So I have this thing. I want to have this epsilon neighborhood and then anti. So that's what I like to construct. And this is what's called the anti-canonical tower. So, yeah, so what is the gamma 0 p to the m level structure? It just gives me dm in the p to the m torsion subgroup scheme of the abelian variety in the modularity theoretic description, and this is going to be like some maximal isotropic. I mean, for the wave pairing defined on this polarized abelian variety. So, so the anti-canonical is the locus where this guy is not only maximal isotropic, but intersects trivially the canonical subgroup, and this thing exists if epsilon is small. In particular, in the ordinary case, they exist, but also when epsilon is small enough, then there exist canonical subgroups, and we can make sense of the definition. So this, and when you take the limit over all m, then you have this anti-canonical tower. And the key point is that the transition maps are going to be sort of relative Frobenius. So maybe the transition maps in this F0. F0 is the limit of this transition maps but these are basically relative Frobenius whenever you go from gamma 0 m plus 1 to gamma 0 p to the m plus 1 to gamma 0 p to the m for every m. These transition maps are going to be relative Frobenius. Well, not literally, but mod p, or you allow some error, so mod p to the 1 minus epsilon, these are relative Frobenius. Or to put it differently, these transition maps are lifts of relative Frobenius. And that basically allows you to prove that this limit is a perfectoid space. in a way similar to the toy example. So pardon?
What is anti-canonical?
Anti-canonical, yes, anti-canonical means that it's a maximal isotropic subgroup which intersects the canonical subgroup trivially. So that's why I call this anti-canonical locus. So this is by definition, anti-canonical locus, which means, so maybe that is, yeah. So this is the main point when showing this guy is perfectoid. But that's step one, so you need to go further. Are there questions? Okay, so you need to go all the way up. So now you can just take the preimage. And now you think about this part. Here, what is the point? All right. You memorized the theorem, I guess. Okay, so step two is purity, and I'm not going to say too much about this, but purity here means that finite et al. Over perfectoid is also perfectoid. And to upgrade the statement, also the projective limit of finite et al. Over perfectoid is perfectoid. It turns out that this map is just the limit, the projective limit of all these finite et al. Maps. Well, I'll correct this statement in a moment, but F is limit of finite et al. Maps. So by this kind of general purity result, you get that this thing is perfectoid. And in fact, actually, you can say better, it went far away again, but these are actually affinoid perfectoid. And so is this one. So these are except that the lie here is that it's finite et al. Away from the boundary. But I declared conveniently that I'm going to ignore any boundary issues. But you need to do some serious work to show that this is actually affinited perfectoid, even if there's some ramification happening at the boundary. Okay, so that's step two. And well, how many steps do I have up to step 5? So we'll see. So what we have is we now went up all the way up, but then it's some small locus inside here. And it's good news. You know that it's a affinoid perfectoid in some open subset, but certainly that's not good enough. So the next step is you construct some topological Hodge-Tate period map. So again, this is some projective system of adic spaces, but you can just take the limit of topological spaces, so this makes sense. And also you can talk about points of this guy by taking the set of points, by taking the limit of set of points at finite levels, but a priori work away from the boundary. So you can do this, and again, on the level of points, as I said, you can make sense of points. The limit exists on the level of sets. And, well, you have polarized abelian variety going to the Hodge-Tate filtration. But the Hodge-Tate filtration only depends on this guy at P, like P divisible group of A. So it's actually pretty obvious that this guy is equivariant for the prime to P hack action, because prime to P hack action literally doesn't do anything, and then it doesn't affect the Hodge-Tate filtration. Also, the equivariance for the away from P action is clear, and then if you really think about this map, how this map is defined, then actually the equivariance for GQP action is also clear. It's just you can just write it down and see. So in particular, it's GQP equivariant. On the level of sets, it's not hard, and it's. You forget about the level structure. You mean level structure at P, or? Yeah, the level structure is used. So maybe I didn't. Before I didn't make a precise statement. So thank you for the question. So the question is about the level structure at P, I believe, and then. Actually, it's an important point that you use the level structure to identify this Tate module with, well, ZP, and so therefore CP to the dimension times 2. So you use the level structure to identify this guy with CP to n. So that's actually why the Hodge-Tate period morphism only exists at the P infinity level, because you need to kind of trivialize this guy so that when you have like this Lie algebra embedding here as a maximal isotropic subspace, then you have a well-defined map into the flat variety. So yeah, thank you for the question. And then the important point is, because we are going to make a topological argument with this map, you need to show that it is continuous, and it essentially follows from the fact that you can construct this Hodge-Tate filtration in families. Not just for a single abelian variety over fields, but actually you can make it work in families, and that basically translates into continuity of this map. So that's so much I'll say about this guy. And let's see how this can help us. Okay. So steps 4 and 5, and may not have too much time for the construction of torsion Galois representations, but we have Q&A session. Maybe that's okay. I mean, I would rather not rush too much, so. Okay, so let's use it. And the way to use this Hodge-Tate period map is you use it to propagate perfectoidness. And you're going to use this GQP action. So to do this, maybe it's good to know that I have this pi ht One very useful fact is that this ordinary locus given by epsilon equals 0, that really maps into the QP point. Well, I didn't really pay too much attention to the base field of FL, but in the Ziegel case, the co-character mu is defined over Q, so this QP point makes sense. And you can show that this is true. And well, ordinary basically means that it's just the product of the étale group scheme times some copies of mu p infinity. So actually, you can just check this quite explicitly. And then there's some intermediate open neighborhood of the QP points. you can find it in a way that its preimage is contained in some epsilon neighborhood for some positive epsilon. So you can put yourself in this kind of scenario that you have some neighborhood here such that its preimage is contained in some epsilon neighborhood. So that's going to help us propagate perfectoidness, because it's kind of like you have the underlying topological space for this guy, but then you want to build a perfectoid structure on this topological space or this space. And this perfectoidness is kind of local property. And we already know that in some open subset, in the anti-canonical locus, you have this perfectoid structure. And by group action, you want to just cover the whole space. Then you have this covering of this guy by affinoid perfectoid. So, and they glue together and to give you a perfectoid space structure for the whole thing. So to make this work, the basic observation is that this GQP action, GQP translates of U, cover the entire flag variety. This is some explicit. This can be shown by some explicit computation. So kind of you can work explicitly, and then by taking preimage, you see that your Shimura variety can be covered by these translates of the preimage, but you can make it even larger. So there's nothing wrong about that. But then this thing is also equal to GZP translate of the anti-canonical locus. I mean, here the basic point is that the anti-canonical locus is like you're preferring a certain subgroup scheme, but by the GZP action, you're basically allowing to be any subgroup scheme, not just the anti-canonical one. So that's basically why this is true. You're going, in some sense, you're kind of permuting all the possible maximal isotropic subgroup schemes. So the condition anti-canonical goes away. So the conclusion is that this is the whole Shimura variety, at least away from the boundary. So as a result, we have shown that this guy is, at least away from the boundary, this guy is a perfectoid. And well, we're almost done. And yeah, you can then, basically extend to the boundary. So, and also it remains to upgrade this Hodge-Tate morphism. So I'll just say here that I'll be brief. So upgrade this pi HT to a morphism of adic spaces, and including the boundary to the flag variety. And yeah, it's not, you can, it turns out that you can more or less recycle the argument from step 3. So you don't need really much new ideas. On the other hand, again, extending to the boundary is an issue. So yeah, that probably I'm not going to say anything more about. So I have maybe about 5 minutes left. So are there any quick questions? Yeah.
A conceptual question. So did we really construct the perfectoid structure, or did we have some kind of adic structure, and then we show that
it's a perfectoid structure? So it's here we have the affinoid perfectoid structure, and then I covered this by translates of this guy. So yeah, so it is covered by affinoid perfectoid.
Yeah, but the adic structure, we add it a priori, and then we show some additional property, which is perfectoidness, or do we really construct perfectoid?
There's no a priori adic structure, I would say.
Okay.
So
okay.
yeah.
But just a projective limit of phases.
Right, yeah, and I mean, this guy is really, this perfectoid space is equal or isomorphic to the limit of the adic spaces at finite level in the sense of Scholze-Weinstein, which is like on the topological space, it is what you want, and then on the level of algebras, it's a weaker statement. It's not isomorphic, but it's sort of a dense image. So yeah, in that sense, it's the limit of adic spaces, but I don't think we have a priori an adic space structure. Yeah. Okay, so what shall I do? Maybe I'll just give a quick outline of what's going to happen for the construction of torsion Galois representations, and then maybe I could say more during the Q&A. So yeah, in this diagram, basically we want to go from the Hecke eigencharacter to the FL bar coefficient Galois representations. So that's part 4. And here, well, what is the main point? What do we want to achieve? Well, given some Hecke eigensystem, we want to show, so given, we want M is, well, mod P of some classical Hecke eigensystem or Hecke eigencharacter. What do I mean by classical? Classical means that it's just some Hecke eigencharacter appearing in the cohomology of Shimura varieties with characteristic 0 coefficient. So that's the classical setup where things are directly related to classical automorphic representations by some sort of Matsushima. But yeah, but as I said, well, it actually is not going to work completely literally. Something like this is going to happen, but up to a doubling in some sense, and in the following sense. Well, given M, let's say I found some classical Hecke eigensystem, then it has to do with automorphic representation of some classical group, and that's basically the self-dual case. And in that case, we are going to have some Galois representation, say rho, and then by taking mod P, what I'm going to get out of this is more like what we want is what I denoted by rho m bar, which is some n-dimensional FL bar Galois representation, but roughly speaking, I'm going to have kind of twin, it's dual, or maybe in the SP2N case, plus some one-dimensional, because the dual group of SP2N is SO2N plus 1, so you expect a 2N plus 1 dimensional representation. So what you want is rho m bar, but then what you're actually getting out of this is rho m bar plus rho m bar dual or something. So there's some algebra argument you have to make but this can be done. That's actually the easier part of the problem. So the harder part is really you want to make your Hecke eigencharacter mod P of some classical Hecke eigencharacter in some Shimura variety. So, and as I alluded to earlier, this kind of connection is made by the Borel-Serre compactification. But up to doubling on the Galois side, or maybe on the automorphic side, is more like taking parabolic induction. It's analogous to that. And once you are there, you are in the game. Now you're looking at the cohomology of Shimura varieties again, and there are things you can do. But I think this is probably a good place to stop. And well, the rest of the argument, if you're interested, ask me, and well, I'll be happy to answer.
Are there quick questions?
I'm interested.
Okay, thank you.
So in the top board, right?
Yes.
The point where you say that the transition maps are nearly like Frobenius. Is it possible to write down those maps, like on the level of like the moduli?
Yes, yes, I can do it. Do you want it now or later?
Later is fine.
Yeah, but I'll just say one word, one sentence, and then maybe I can say more. The basic principle is that the canonical maybe a few sentences. Canonical subgroup is constructed to be a lift of the kernel of Frobenius, and what that means is that given an abelian variety, A modulo its canonical subgroup is going to be Frobenius. And basically it follows from this fact eventually. The modding out by canonical subgroup is a Frobenius map, but for some technical reason, you prefer to do anti-canonical rather than canonical. But that's the basic idea. Yeah.
Before we take a break, can I ask you why we worked so hard to prove that it is perfectoid? Like why is it so important?
Right. Yeah. So it allows us to use it in the construction of Galois representations. For instance, you're going to have cover this with affinoid perfectoid, and using the Hodge-Tate period morphism, you can find actually you can pull back some explicit covering in the flag variety to get a nice check covering here. But then this covering is not very nice actually. Because of this equivariance, it's going to be it's going to be stable under the away from P Hecke action. That's one important thing. And the second important thing is that you have an affinoid perfectoid, and these guys have vanishing properties, cohomological vanishing properties. So you can basically reduce your problem to computing H0 of these affinoid perfectoid covers. And once you're there, then you can pull some other tricks like fake Hasse invariance to complete the argument. But yeah, that's why it's important. It allows you to compute the a priori complicated cohomology with some easy kind of topological covering consisting of affinoid perfectoid, coming from the pre-image of the Hodge-Tate period morphism.
You can't carry on this type of argument with the projective system.
Yeah, so I guess the question is, can we carry on this argument with the projective system? And I guess what you mean is perhaps the classical automorphic representations are those at finite level, but then Hodge-Tate period morphism only happens at P infinity level. So can you actually go down to finite level to relate back to classical automorphic forms? And yeah, this can be done, but yeah.
And I think another reason you want it to be perfectoid is you want to, for mod P coefficient, you want to use the primitive comparison theorem to relate a cohomology of some local system with a coherent.
But yeah, you need the comparison theorem, but yeah, so the question is, yeah, do we also use perfectoidness for a comparison theorem? And I think you're alluding to the kind of comparison theorem, which I was going to state if I had time, but you have the Shimura variety with FP or FP bar coefficient, and then you can switch to some Shimura variety with in Scholze's notation something like I plus over P. So like you go from like some étale cohomology to some sort of analytic shift cohomology, but I think this type of theorem is also true for proper rigid analytic varieties. But yeah, we can look up. But for the comparison, this kind of comparison, I don't think you need perfectoid.
Yeah, I think it's not really good to work with whole towers because you really need to take completions of the function because like eventually what we want is complete cohomology. So it's like the tower of cohomology and eventually we complete.
Yes, yes.
And if you only take towers of adic space, it doesn't give you structure shift, and you are not taking the completion of the structure shift. But now, if we pass to perfectoid Shimura variety, its structure shift is already completed. And you may think maybe you can just take inverse limit in the adic space, in the category of adic space, but the problem is this thing is not really well behaved. I don't think there's arbitrary limit in this category, and it does if it's perfectoid. So yeah, I guess it's some subtlety about adic space. Well, then if you use perfectoid, things is better behaved.
Well, we can maybe discuss more in the Q&A session.
Okay, yeah, let's take a break and come back.